students. We are going to study electronic devices, and in this video we will be discussing formation of energy bands in conductors, semiconductors and insulators. So let's start with formation of energy bands in solids. You're already aware that an isolated atom has well-defined energy levels. I am showing you an atom with positive nucleus and orbits around it. All the valence electrons have well-defined energy levels according to quantization condition or quantum mechanical laws. But when large number of atoms come together to form a crystal, then these charged particles, electrons and the positively charged nuclei, they are very close to one another, and then they influence or interact with energies of one another, and as a result the energy get modified, and energy of a crystal are divided in two bands called valence band and conduction band. The energies of outer electrons are modified, but the energies of inner shells, they remain almost non-affected because they are well shielded. So the modification is not appreciable in case of energy levels of electrons in the inner shells. Energies of outer shells are modified. And to understand it further, let us take example of silicon crystal. Its atomic number is 14 and electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p2. You can see that the outermost orbit has 4 electrons and it requires 4 more electrons to complete its outermost shell or octet. So it shares its electrons with 4 more silicon atoms in covalent bonds. Let us try to understand this by using this graph. This is a graph between interatomic spacing in crystal and energy levels. See here, the inner cores is given 1s2, 2s2, 2p6, and the outermost shell is shown here with 3s2, 3p2, and when the spacing is large, see beyond C and D, the energies are well defined. But as the atoms come closer or spacing decreases, the energy levels get mixed up. You can see at between A and C, energy levels are mixing up, but the inner shells are not affected. Only the outermost shell is affected. Now, when it reaches an equilibrium position, OA, this separation is called lattice constant also. Then at that point, the energy levels get separated into two bands called valence band and conduction band. The separation between these bands is called forbidden energy gap. Now these energy gaps are not uniform or homogeneous, rather they consist of very closely spaced energy levels called the spacing between energy levels is of the order of 10 raised to the power minus 23 electron volt. So these bands consist of discrete energy levels, though very closely spaced. Now, when we say that an electron is in valence band, it means it is tightly bound in covalent bonds. And when we say that an electron is in conduction band, that means it is free from its parent nucleus and it is available for conduction. Now, the type of material depends on the gap between uh, valence band and conduction band. So, let us first take energy band diagram of metals. Now, here the separation between valence band and conduction band is very small, or they overlap. So, the electrons are easily available for conduction. They literally overflow from valence band to conduction band. So, the electrons are easily available for conduction. Therefore, the metals are good conductors of electricity. The highest energy level filled at absolute zero temperature is called Fermi level, and that energy is called Fermi energy. Now let's take the example of a semiconductor, the energy band diagram of semiconductor. Now the separation between valence band and conduction band is less than 3 electron volt. For example, for silicon it is 1.1 electron volt, and for germanium it is 0.74 electron volt. At absolute zero temperature, all the electrons are tightly bound in their covalent bands, or they are in valence band. Therefore, no electrons are available for conduction, or conductivity of semiconductor is 0. But at room temperature, when some of the electrons gain enough thermal energy to reach the conduction band, then the conductivity of semiconductors increase. Now, when an electron jumps from valence band to conduction band, it leaves a vacancy of electron in valence band. This vacancy is treated as a positive charge and it is called hole. Now, energy band diagram of insulator. Here, the separation between valence band and conduction band is very large. It is greater than 3 electron volt. For example, for diamond, it is nearly 7 electron volt. Now, here, the electrons are tightly bound in their covalent bonds. So, they cannot leave the valence band and they cannot jump to conduction band. So, the conductivity of insulators is very poor. Now, electrons and holes, as I have already told you, holes are nothing but absence of electrons or vacancy of electrons. So, holes are treated as positively charged. They are also charge carriers. Now, what happens that when a hole is created, the electrons from neighboring bonds have tendency to jump into these holes, and this is called electron hole recombination. Now, to understand it, let's take up an example of a pure semiconductor crystal, also called intrinsic semiconductor. So, here is an example of germanium crystal. Its 4 valence electrons are shared with 4 neighboring electrons to complete the 4 neighboring atoms to complete the octet. Now, when the crystal gains some energy, some of the electrons break the bonds and become free. So, a hole is created. Now, some electrons have tendency to jump into these holes. It is called electron hole recombination. So the position of hole keeps changing from one place to another. Now look at this energy band diagram. You can see electrons in valence band. They are jumping to conduction band, creating one hole in valence band. Valence band means covalent bond. One more electron hole pair and one more. Now, this electron from conduction band jumps into the hole. This is called electron hole recombination. Now, so the number of electrons and number of holes are equal. The conductivity of pure semiconductor is very low. Now, to increase the conductivity, we need to add some impurity to pure semiconductor, and this process is called doping of a semiconductor. The impurity is called dopant, and it is added in very small amount. It is of the order of 1 ppm or part per million. Now this impure semiconductor is called extrinsic semiconductor, and different methods of doping are like heating the crystal in presence of dopant atom, adding impurity atom in the molten state of semiconductor, bombarding semiconductor by ions of impurity atom. Now extrinsic or impure semiconductor, they are of two types depending on the type of dopant atom. Now here this germanium crystal is doped by using a pentavalent arsenic atom. Now arsenic atom has 5 valence electrons. Now these 4 electrons are shared with the neighboring germanium atoms, and 1 electron is donated for conduction. So this arsenic atom is also called donor atom because it is donating 1 electron, and since it donates its electron, it behaves like a positive ion. Now these donated electrons have high energy, and their energies are just below the energy of conduction band. So these donated electrons populate an energy level just below the conduction band. This level is called donor level. Now it is very easy for electrons to jump from donor level to the conduction band. Therefore, the conductivity of N-type semiconductor is much larger than the pure semiconductor. And here the majority charge carriers are electrons and minority charge carriers are holes. Now the product of number of electrons and number of holes is constant, and this product is equal to Ni square, where this Ni is number of intrinsic charge carriers or number of charge carriers in pure semiconductor. See, the NP is constant. It is called rate of recombination. Now P-type semiconductor. Here the impurity is trivalent and it has 3 valence electrons. So it shares these 3 electrons with the neighboring germanium atoms, and there is vacancy of one electron. That means it has one hole, and the neighboring electrons will have tendency to jump into this hole. As a result, this indium will behave as an acceptor atom, and it will behave like a negative ion. So, the electrons from valence band have tendency to jump into holes. An energy level is created just above the valence band, where the electrons from the valence band jump to, and this level is called acceptor level. And from here it is very easy to jump to conduction band, and electrons also move from one hole to another. So we can say that large number of holes are available, and the majority charge carriers are holes and minority charge carriers are electrons. And here also the product of number of holes and number of electrons is constant, and it is equal to Ni square as in the previous case, and Ni is number of intrinsic charge carriers. So let's talk about electrical conductivity of semiconductors, or how a semiconductor behaves in an electric field. So when a semiconductor is placed in electric field, the electrons will move opposite to the direction of electric field, and holes being positively charged will move along the direction of electric field. As a result, they both produce currents along the same direction. So the total current passing through the semiconductor is sum of these two currents. Now current due to hole and due to electron are given by this relation N E A V H or V E. The same relation that you have done for drift velocity for current and electricity. So the total current is sum of these two currents. Now let's talk about mobility. Now mobility is defined as the drift velocity per unit electric field. And the important point to note is that electron mobility is higher than the hole mobility. Thank you.